Ajay Gumadi from the networking team in Windows Server. If you have used DNS, DHCP or various remote access solutions such as VPN server or direct access or IPAM from Microsoft, those are products that were built out of our team in the India Development Center at Hyderabad. Today I am going to take this opportunity to talk to you about some of the advances in the networking space from an industry standpoint. We have been building cloud networks for quite some time now, and we understand some of the problems we face, and I'm going to highlight some of the problems and how we solve them. This session is useful for you if you either are interested in knowing about the advances in networking, or you are a technologist looking to enter the networking space and want to disrupt the networking industry in some way. With the advent of software defined networking and the pervasive availability of software skills, opportunities that were previously available to some of the deep pocketed players in the industry is now available to someone with the skill and the entrepreneurial mindset. So first I am going to cover the network, what we call as the legacy network, which has existed for the last 4 decades or so and largely remained unchanged, and it still continues to exist in some of the more static environments. I am going to talk to you also about the challenges that we see in those environments and how software based networking presents an opportunity to solve that. So what is the basis for much of our presentation, much of our learning here? We have been building the Azure cloud for quite some time now, and it is one of the largest public clouds out there. We have about 90,000 customers signing up to the cloud every month. So in doing so, in building one of the largest clouds and in keeping the availability up in the high 9s, we have learned a few lessons, and I'm going to distill some of that through the rest of this presentation. So anytime you make a call via Skype, or you check your email via Hotmail or Office 365, or you track your customers via Dynamics, or play games on Xbox, those are services that are available to you from the Azure network, from the Azure cloud. So where is Azure and roughly what is its size? Azure is present in almost all of the areas where your users are located, with the possible exception of Africa. We have partners managing our cloud in China, and we have a separate cloud for the federal agencies, for the state and local agencies as well. For some of you who have never visited a data center, just to give you a sense of size, a data center is roughly about the size of a football field. And to give you a sense of perspective, you can park 2 jumbo jets comfortably, one after the other there, and that's one building. And you have about 16 buildings in an Azure data center region. And each of these data centers, as you look, can host about 600,000 servers. Moving on to the legacy network, the illustration that you see on your screen is the network as it's been for a while. You start off with a router, you connect it to the internet, and you add a firewall behind it, and you add a core switch behind it. So as you start adding more and more capacity, depending on the capacity, you add particular elements on the network. So if you were to add a large building per se, you would add a distribution switch, and you add a floor in that particular building. You would start with an edge switch, and you connect all of these switches, whether they are distribution switches or the edge switches, back to the core switch. And as Wi-Fi came along later on in the game, you start adding them as leaf nodes. So your computers, your Wi-Fi access points, printers, these are all leaf nodes. The early data centers also followed pretty much the same design. And so what you see right now is the capacity addition is asymmetric, and we'll get to what that means later on in the presentation. And the performance of your application is dependent on where it was added in the particular network. If it was added on one switch, the latency it introduces is going to be substantially different from if it was added at a different switch. So these are problems that you need to solve, and we'll talk about why in the subsequent portion of the presentation. The other points so we moved from the networking as it exists on a legacy network to more of a hierarchical layout of the network, or the topology of the network. So if you look at this picture, you have the aggregation switches on top, and these aggregation switches connect to a bunch of core switches, and from the core switches you have a bunch of hosts, and you have the ultimate applications are hosted on virtual machines that are connected to this. So let's assume that for the sake of example, let's think of this as a university, and let's again, for sake of simplicity, let's think that there are 3 classes of users. The first one is the finance department of the university, which is denoted by the orange virtual machines, the faculty, which is denoted by the red virtual machines, and the students by blue. Now obviously you don't want any one class of users interfering with the activities of the other class. For example, nobody in the university outside of the finance department wants anyone to have a sneak peek into the financials of the university. Similarly, the faculty definitely wouldn't like or wouldn't be too happy with any of the users of from the blue VMs trying to access their grades or tamper their grades or look at the exam material in advance. And so how do you do this on a regular network where all of these virtual machines, whether they are from the students or the faculty, they are all on the same set of hosts? Well, in the networking world today, we deal with them using VLANs. So basically, you see the small dots associated with each of these VLANs, and now you configure each of those switches everywhere where the traffic touches. So if you see the switches and the hosts, you see the dots, the yellow dots or the blue dots. Now let's say that I were to add a red virtual machine, the faculty virtual machine. Now we add the configuration on all of the switches along the path wherever that particular traffic goes. So as you will see, irrespective of whether I add a faculty machine, I remove a student machine, or I replace one of the switches with other switches with another switch, I will have to go about reconfiguring the entire network. So in a sense, it is easy to see that networking is fairly brittle. A small change here and there can have a massive impact down the line. Let's move from the networking to one of these individual devices. Let's drill down into them. The big gray vertical column that you see is the high-end router. When it's fully loaded, it's a couple of $100,000s at least. And the blue and pink illustration that you see next to it is a representation of the protocols it supports. A typical router usually has between 4,000 and 5,000 routing protocols and standards, and has about 20 million lines of code. So in essence, it is a smaller version or a meaner version of the operating system. And let's say you want to add a particular protocol. How do you go about it? Well, even though it has an operating system, you don't have access to it. The way you get around to it, the way you get your features added into it is you talk to your vendor. Your vendor goes to a standards body. The standards body takes between 2 and 3 years to standardize on the particular protocol, and then after that it takes between 18 months and 3 years to create the ASICs. And once those ASICs are done, it takes some finite amount of time to get the protocols into your device. So as a university administrator, you notice that a lot of your students are accessing streaming media, and your network isn't necessarily the fastest for streaming media. There's a lot of buffering, etc. And one of your professors decides, hey, he has come up with a new routing protocol. How do you implement that? Well, just because you know some Perl or Python and you can write programs on your computers, the same knowledge cannot be extended to to the networking devices. So we talked about the networking side of it, the gear side of it, or the vendor provided equipment side of it. Let's also look at the human part of this network. So Azure is adding about 90,000 users, and let's say a small fraction of these users want to make a set of changes on their network. If you look at the illustration and the changes, the potential changes could be someone wants to add a firewall rule, someone wants to add a load balancer, it could be one of many things. And let's say there are only about 10,000 changes that are required on the network, and for each of these changes to be reflected on the network, each of these provisions requires about 20 commands on the network. That we see from the illustration is about 200 commands that need to be run on the device. Now even conservatively, let's assume that it takes us only 1 minute for each of these commands to be run. To complete all of these activities, all of these changes by the end of the workday, it takes you about 420 network admins. It's not only the number of network admins and the cost therein, but it's also the monotony that is introduced and how error prone this operation can be when you repeat it day after day after day. So quickly to summarize on the legacy network what we have covered so far, provisioning is a very slow activity. You have seen that in the example of VLANs. Now if you contrast it with storage and compute, both of those can be provisioned in a matter of minutes. But on the networking side, it takes order of weeks. So from the time you ask your network administrator to make a particular change to the time you get back a confirmation email that hey, everything is set up, it can take almost 3 weeks in many organizations. The existing network, given its history, is designed for a different environment, a more static environment, an environment where you know beforehand what applications are going to be installed, what applications are needed, what their traffic patterns are, where exactly they're going to be installed, etc. If any of these change, at this you are expected to redesign the network to get optimal performance. Manageability is another big problem in the industry. If you look at even though we talk about network management, it's really a device by device management. If you had to manage 10 different interfaces, you would have to individually log on to all of those devices and make those changes, not necessarily a very scalable operation. That also means a confluence of all of these factors leads to very low utilization of all of these devices and hence your network. Now, these are what we discussed so far are the problems that we see on the network. Now, our usage patterns have also changed over the last decade or so, and we'll talk about some of those. So, the top chart that you see is the traffic that's going on the network, the data center traffic, and as you can see, it's increasing. So, right now in 2016, the projection is we will have about 6.6 zettabytes of traffic. Just for perspective, or for those who don't know what a zettabyte is, so you have kilobytes, 1,000 of those kilobytes is a megabyte, then you have gigabytes, terabytes, petabytes, exabytes, and zettabytes. Now, let's consider the next lower value, that's exabytes. So, everything that mankind has ever spoken since they started speaking, that's only about 5.5 exabytes. So, a zettabyte is 200 times that, and really we are right now communicating in 6.6 zettabytes this year. And we have also seen an increase in the number of devices, number of connected devices. It's no longer limited to those servers and those laptops and those wireless access points. You now have wearables, you have your smartwatches, phones, tablets, and Internet of Things. And why is this important to us? As you add more and more devices, roughly the finding is that for every 150 devices that you add, 150 connected devices that you add, a server is being added somewhere. So, you will correspondingly see in this server install base chart below that the number of servers is also increasing. And the interesting part is all of these servers are not necessarily being added in the traditional data center, rather they are going into the cloud data center, and that impacts how the traffic is changing over the network. So, on this slide you will see the data center traffic patterns. There is a slide from Cisco. Basically, if you again go back maybe 15 years or so, bulk of the traffic on the network was traffic from the user to the internet or from the internet to the user. So, things like FTP, things like web page access, etc. This is what we call north-south traffic, and that was about 80% of all traffic. Fast forward to today, and a bulk of the traffic is within the data center, that is from one server in the data center to another server in the data center. That is what we call as east-west traffic, and that's about 75% of the traffic. Now, how do we know that this traffic exists? So, just open up your smartphone app and your social network app on your smartphone, and it gets you all the information about your friends and what they have been doing. But behind the scenes, the server that your app has reached out to is talking to a whole lot of servers. It's first trying to authenticate you, then it's going to multiple other servers to find out about your friends, who your friends are. Then it's going to storage servers trying to connect to and get all your photographs and who has liked them, etc., and then friend feed. So, it's compiling all of that information behind the scenes, and all of that adds to a lot of east-west traffic that changes on the network. Networks in the past were also defined by a particular perimeter. So, everything, let's say, within a compound wall or roughly define the network perimeter. Now, if you look at this particular illustration, you on one side you have the traditional network, which is there is an organization which has a certain number of users. Each of those users has a certain number of desktops or servers. There is an operating system that is approved by the admin that's installed on that, and then you have applications that were either installed by the admin or approved by the organization, and the data generated by each of these applications or by the users either resided on the file server or on the local hard disk. And basically throughout all of this, you see a thread of control. There is an element of trust, a certain degree of trust between all of the elements. You know who is doing what, and you know what elements are in the network, and there is a certain degree of control. Now, if you look at the diagram on the right side, that's the modern network. Your network administrator or your organization is no longer able to limit and say thou shalt use only one particular OS, or you should not be able to bring in phones, or and that's on the OS front. Now, look at the applications. Your applications are no longer just limited or confined to those that are installed on your desktop. You have SaaS applications that could be located and hosted in data centers several thousands of miles away. And then your storage, it's no longer just limited to your local disk. It could be on OneDrive, it could be on it could be on Google Drive, it could be on Dropbox or Box, anywhere else. And your network also is no longer just limited to that one area where your organization is located. If you are a university, for example, your university may have relationships with other research institutions in the area, and depending on the nature of relationship, your network may expand or contract at any given point. So it's very difficult for you now in a very fluid environment to define and say this is exactly how my network look like, or these are my applications, and the network must be able to scale to that. Let me move from the technology side to to an economic point of view. We have all seen the cellular, we have all been using our cell phones for quite a while now. If you look at your voice bills for maybe the last 4 or 5 years, you will see that that we are paying roughly the same amount as we were paying then. Your voice traffic definitely hasn't increased, but there are a lot more services that the cellular provider is providing. Maybe is moving from 3G to 4G and beyond, providing newer features, etc. Now, so voice traffic is declining. So where are they able to get money for all of this? How are they making those investments? Do you think it is SMS traffic? Well, really not. If you look at SMS traffic from, let's say, UK in 2011, they were about 27 billion messages sent in UK in that year. Now, today there are only about 20 billion messages sent globally, and a bulk of the messaging is happening via other apps, WhatsApp being one example, which probably sends about 60 billion messages a day. Now, even though all of these WhatsApp and other operators, over the top operators, are sending all of these messages, they are sending the messages over your cellular network, but your cellular network is not able to monetize them. If you look at the ISPs also, you have the same case. The bill is almost the same, but the bandwidth has doubled, more or less doubled in the last 5 years. The amount of free usage has also increased, but their costs continue to increase. Every truck roll costs them a lot, and so these folks are in a situation wherein the costs are increasing at a higher rate than the revenue, and something needs to be done here. Virtualization is another phenomenon that has had an impact on the network. A few years ago, if you had a mission critical application, you got a server, you installed the operating system on the server, and then installed the app. Now, you would dare not install a second application on that particular server. Why? Because it might have a patch level conflict, it might have a dependency, a shared library dependency, it might have registry level conflicts. And so the industry responded to this problem with virtualization. Basically, you have a thin layer called the hypervisor, which resides over the physical server and exposes all the properties of physical server to entities above it, which we call virtual machines. Each of the virtual machines can have its own OS. Virtualization has several advantages. Primarily now, in the previous server world, in the server only world where the server was hosting only one particular app, the server utilization was very low. In most cases, it was around 6%, and that was a peak utilization in many cases. Now, what you're able to do is you're able to pack many more applications and many more servers onto one physical server, so your attendant needs of cooling goes down. You're able to isolate your applications better. And now people figured out, hey, virtualization provides a mechanism to separate the application from the physical hardware. So with virtualization now, you're able to pack many more virtual server instances on a single server. So while the previous utilization of the server was very low because it was dedicated to a single app and the utilization was around 6%, now you can get it up into the high double digits because of virtualization. A number of virtual machines can be packed onto a single server, and that basically means smaller data centers. You can consolidate on the energy utilization, on the power, on the cooling utilization, etc. While the virtualization provides the same benefits as what was available on physical server. So with virtualization, you have been able to separate the dependence between the app and the physical server. And then people decide, hey, now I have a virtual machine, I can move it to a new server. I buy a new faster server, I can move this virtual machine. And then people start building on that particular idea. So people then start saying, let me move this not just across a server within my enterprise, let me move it across data centers. And then the cloud operators started emerging. These are people who are able to build out data centers at massive scale and get economies of scale there and pass on some of those benefits to their end users. At one point, this business was growing so fast that the only thing that was stopping them was the ability to procure new servers, rack those servers, and connect those servers. And then you see this picture on the screen, which is a pod. It's a shipping container where the OEMs, which is the device makers, the PC makers, bring the servers, bolt them on, a truck comes in, takes the pod, brings it to your data center site, and all you have to do is connect power, connect cooling, and you are in business. You can start servicing your clients at this particular point. These data centers are increasingly software controlled, make do with a very small amount of human resources. Maybe in their cases wherein the data center is run by 2 or 3 people, and even these 2 or 3 employees are primarily looking up a console, looking for, hey, warning signs, or walking around and seeing, hey, this red blinking light, taking out the server and putting a new server in. So this is pretty much how the cloud evolved. Azure is one such cloud, and you have clouds from competing organizations. There are several benefits to cloud as you go about it. One is it's a shared pool of resources, unlike the physical server world wherein CPU was dedicated to you and memory was dedicated, storage was dedicated to you. It's a shared pool from which you can draw resource as you go. The other advantage is you are built on a per usage basis. You can also real time scale up and out. So during the holidays, if your business is doing well, you can scale up, increase the number of servers, and correspondingly scale down. It also offers in many cases the advantage of self-service, which is going back to the previous instance wherein I mentioned it can take you about 3 weeks to configure. Here configuration of a network is about 10 to 15 seconds at most. What you see on your screen is what we call a class network. So previously I mentioned at one instance that the capacity addition is not symmetric, and depending on where your application is connected, on which switch it is connected, performance can vary. In this particular diagram, you will see that we have 3 layers of switches. We have the core switches, and below that we have the spine switches, and then the top of rack switches. And you will also see there is a pattern. Every switch at every layer is connected in a full mesh format to all switches above it and beneath it. So if I have 2 servers, and I would now logically have to connect them at the leaf switch, at one of the leaf switches, and these switches are basically, these servers can communicate with each other, and they are basically one hop away. Then that introduces a certain amount of latency. Now let's say later on my business grows and I want to add a 3rd server. The 3rd server can be added at the far end of the data center. Now in this particular case, you see that because of the connectivity mesh there is a constant number of hops, irrespective whether the additional server is nearby or at the other end of the data center. So in this particular case, any server is at most 3 hops away for you. So what is the solution? How do we go about building a network that addresses the challenges that we have seen and also meets the new demands that we have seen in terms of traffic patterns, etc. And one such solution that has come about in the recent past is software defined networking. The definition of software defined networking is on the screen. It's from Wikipedia. But more than a definition, I would like to focus on a couple of things. It talks about abstraction of high level functionality. It talks about decoupling, and those are the words that we want to stress on, and that will help us understand how software defined networking is implemented. Basically think about it that with software based elements, you should be able to switch, you should be able to route, you should be able to secure and manage your network. That's the essence of software defined networking. So to understand the concepts of decoupling, etc., let's go back into its history. So in 2008, a couple of researchers, Scott Schenker and McKeown, wrote up a paper called programmable networks, and they talked about this protocol called OpenFlow. And here they talk about a separation of planes, 2 abstract planes, a control plane and a forwarding plane. And to understand this separation of planes, let's look at the traditional network. Here you see 3 devices, and what they do is they talk about this particular device and they break it up into 3 planes. The lowermost is the data plane, and the data plane is responsible for forwarding packets. Takes packet from one place, puts it at the other end of the device. The control plane decides how the packet should be forwarded. So it basically instructs the data plane saying, hey, this particular packet coming in, drop it, or this particular packet that's coming in, forward it on a particular interface. So traditional routing protocols, whether it's BGP or rep or whatever else, they fall into the control plane. And then you have a management interface, which is an interface that you use to configure the device. And all of these devices are managed by an element management system or network management system. What the researchers do is they propose an OpenFlow enabled switch. Basically they take a data plane, a switch with a data plane only, and add a flow table. So there is no control plane or no need for a management plane within that particular switch. Now the flow table, given that it doesn't have a control plane, the controller, there is an element called the controller that sits somewhere in the network, and that provides the instructions or that provides the flow tables, and the flow tables ultimately determine how the data plane is going to act on the incoming data. So they talk about an open flow switch, and then they talk about open flow enabled switches, which is enhance your existing networks or enhance your existing networking switches with a flow table, and hence you are ready for SDN. The open flow switch specification is published later that year, and the organization or rapport around that organization grows. Subsequently, around 2012 or so, there is a company called Nicira that comes up with a network virtualization platform, and this is a slightly different take on things. Rather than focusing on the hardware, it takes an overlay approach. So it talks about building a network that is above the physical network. So the routers, switches that you see are your physical network, and they talk about a virtual layer above, and all of the networking happens at this particular layer. Again, looking at the network, so this is your traditional network with the hardware elements, and then remember the hypervisor we talked about in the virtualization case. Each of these hypervisors has a virtual switch. The virtual switch is closer to a data plane and receives instructions from the controller. These virtual switches can form a mesh. Now in this particular setup, the physical hardware is primarily relegated to hardware function. Now continuing on the progress of SDN, VMware acquires this company called Nicira, and later on there's a different company called Big Switch Networks that announces an SDN controller. They call it the Floodlight controller, and the big change with this Floodlight controller is they standardize on the interfaces. So previously when we talked about a vSwitch, it had to be a particular vSwitch that complied in that architecture, or an open flow switch. So with this Big Switch proposal, you're no longer limited to those to a small set of devices. You can basically bring in devices from any vendor, any networking vendor, as long as he complies with or is able to take instructions from a southbound API layer. And so you can build a heterogeneous network now. And on the northbound too, they've taken the management plane and replaced it with a bunch of apps. So remember the previous example wherein I mentioned the administrator wanted to optimize his network for streaming media. Think about that optimization as an app, and so you can build multiple apps on an app platform because the API is consistent across them. So that's the big switch, that's the big change that came about with SDN. A couple of other industry movements. Open Daylight is a standards body that was formed. Cisco, with Cisco's backing, Microsoft was also one of the members, and VMware, which had previously acquired Nicira, now starts selling it as NSX. Cisco did a spin-in of its Insiami and incorporated that SDN functionality, which is ACI and APEC controllers, into the Nexus 9000 series of data center switches. So this is how the SDN network looks like today. You have a central controller. So previously we had the routing protocols that were running on each particular device, and now you have one central controller across your network, and then you can use that controller to manage your existing hardware elements, your router, switches, etc., provided they have an agent, or you can manage virtual overlay networks using vSwitches. A controller can also manage a third party controller which may be managing proprietary elements. Given that the controller has both standardized interfaces on the northbound and the southbound side of it, you can build apps easily. You can build apps and sell the apps easily, so you can effectively create an app marketplace there. So what are the benefits of control plane? So if you look at the traditional routing protocols, many of them have, while these are distributed protocols, they have a very local sense of state. They know what's going about in their immediate neighborhood. Whereas with a central control plane, you know end to end how the network is, what's the bottlenecks, etc. So you can route around that. You can better optimize your network traffic. You can do things like end to end quality of service. You can provide security restrictions via access control lists, not only at the egress points and the ingress points which we currently have, that's at the edges of the network, but anywhere on the network you can now have security restrictions, and you can implement these networks using devices from multiple vendors. The other big change is if you wanted to have a firewall in front of your application, well, basically you had to take the firewall and put it in front of the application, or you wanted a load balance. Now you can have your application anywhere in the data center, and via software you control the flow and you're able to place your workloads anywhere. The biggest change that I think in this particular case is innovation. It allows the user, it allows independent evolution of the data and control planes. fundamentally different vendors can work on and iterate on data plane and control plane, and things can evolve there. So let's say I have a network that is for some time of the day doesn't receive a lot of traffic, and there are a good number of devices on that network. So using a control plane, I can basically shift the path during that particular point of day and shut off this entire equipment. So that's an energy management use case, and there are a lot of other use cases that you can build upon. SDN also gives the users a lot of choice. You're no longer restricted to that one or two vendors equipment. So in this particular case, I have again the usual set of devices with the 3 planes between them, and I decide, hey, I'm bringing in a controller. I don't need the management plane on each of these, or I need a lighter version of management plane. So I take the management plane out. Next, I have the control plane. I don't need the distributed control plane. I can have a central control plane thanks to SDN controller. So I take that out, as seen in the illustration. And now, so the management plane is reduced to a bunch of apps, and then you have control plane. So basically what you have on the device is just the data plane, something that forwards traffic, takes incoming traffic, determines where to send it out, and you don't need very expensive devices for that, for devices that are just doing forwarding functions. And this is what we call the bare metal switches or merchant silicon switches. A lot of the data centers that are being built today are being built around data center switches, because remember that earlier diagram wherein we talked about a router having 4,000 to 5,000 protocols. Well, you don't need all of that, and hence you don't have to pay for all of that. You can build data centers at lower cost, and you can customize it further. Over the next few slides, I will take this combination of an SDN controller and a commodity switch or a merchant silicon switch, or you can even think about using a virtual overlay, and see how you can implement various networking functions. So here I have taken a low cost merchant silicon or bare metal switch. I have a controller. I have 3 users. All of these users are trying to access a web based server. Let's call the web server www. Does anyone have an idea of what the load balancer does? Basically, a load balancer helps you evenly distribute traffic. There are several load balancing algorithms that determine how the traffic should be distributed. So in this particular case, let's say the users come from the 3 users send their request to access a particular web page. The controller takes the input from the switch and says any traffic coming from user 1, send it to server 1, that's labeled www1, and from user 2 and 3 to servers 2 and 3 correspondingly. So it basically sends a flow table to the merchant silicon switch, and using a low cost switch, a commodity switch, you basically implemented load balancing on this. So that there you see how the traffic was distributed. The next one is firewall. Again, in this particular case, I have 3 users, and I trust user 1 and 3. User 2, I definitely want to inspect that particular traffic, or basically I want to drop it first, inspect it, and later on allow. So in this particular case, the controller has put out the traffic comes into the switch. The switch looks up its flow table which has come in from the controller, and it notices that any traffic coming from user 1 to server 1 can go through, but any traffic coming from user 2 should be dropped. So as you will see, the traffic coming from user 2 is sent to the SIEM server, which is Security Incident and Event Management Server, and that helps in the evaluation of inspection of that particular traffic. In the third use case on traffic visibility, I have 3 switches. Switch 1, switch 2 are communicating to each other, and I can allow traffic coming in from switch 1 to switch 2, whereas traffic coming in from switch 2 to switch 1, I want to inspect it, again building on the previous use case. So basically the traffic comes in again into a commodity switch. The network controller, the SDN controller, plumps a flow into the network, and basically what the flow says is any traffic coming in from the switch 1 to switch 2, please allow. Anything coming from switch 2, allow, but also keep a copy of it. So what it does is you will see that the traffic coming in from switch 1 has gone to switch 2, but traffic from switch 2 is now replicated. A copy of the traffic is going to switch 1, but a copy of it is also going to a traffic analysis inspection server. This is another interesting area where some amount of activity is happening, some amount of research activity is happening, and there is obviously a scope for a lot more. So you will see here that there is a data center with 3 different racks, and there are applications on each of these racks. So you will see that on rack 1 you have a web server www1 connecting to the DNS server. So there are a lot of network calls there. There is the rack 2 which has a student library, which has a student directory and the checkout machine, wherein students come in and want to check out a book. It checks with the student directory and sees, hey, has this person paid the fees? Is he eligible to make a book checkout? So you see a lot of communication going on. And then there is a third class of traffic, which is the mail server is located on rack 1, and the front end server, that's how you and I access that particular mail server and check our mail, that's the OWA machine that is located on rack 2. So over a period of time, the controller understands what's the traffic on this particular network. It notices that there's a lot of traffic between Exchange server and the OWA server, and these are fundamentally located at different places. So performance can be improved. So it orchestrates the movement of virtual machines from rack 3 to rack 1, thereby improving performance. So the network controller in this case determines that, hey, there's a lot of traffic flowing from rack 1 and rack 2, and it orchestrates the movement of the virtual machine, the OWA virtual machine, from rack 2 to rack 1. And so you will be able to see much faster performance there and much lower load on the rest of the network. We have talked about virtual switch a few times before. Basically, think about it. Previously, if you had a bunch of physical servers that were trying to talk to each other, all of these had cables going to a physical switch somewhere else. And now what you have is, with virtualization, you are seeing that the network card in the server is experiencing the same traffic patterns as your physical server. So basically, the virtualization vendors have put a virtual switch in in the hypervisor, and Microsoft has a vSwitch. So we have an SDN vSwitch in 2016, and we have a virtualization vSwitch in 2012 R2. The virtual switch provides capabilities such as isolation. Remember that that example of the faculty network and student network, that's possible right at the virtual network. And all you have to do is call an API. You don't have to go and plumb half a dozen places around the network. You can do more advanced things. You can do traffic management. You can do quality of service. You can do more advanced flow management. And more importantly, it allows you to build up experimental networks. So if a university researcher or a lab wanted to build up an experimental network and see how the network reacts to certain kinds of protocols, certain kinds of traffic, virtual switch enables that. The other big area that will see a lot of commercial activity is network function virtualization. Your traditional routers, switches, etc., that your telcos use. Now these folks have a lot of capital investment in the networking gear, whether it's the telco gear or the traditional networking gear. Adding one more equipment not only adds cost, it adds operational complexity. And how do you deal with all of this operational complexity and increasing cost when your ARPU, the average revenue per user, is more or less same? There isn't a whole lot of user growth at the other end. So these organizations are increasingly moving to software-based appliances. So you have software-based routers, software-based switches. So this slide just talks about some of how the telcos are increasingly moving to software. And if you go back, now let's say I wanted to provision a particular user. I don't have to have a truck roll. I don't have to send one of my employees to provision the particular user. It's just an API call from a central location from my data center that goes and says, allow this particular user, or enable this user for 5 Mbps or 20 Mbps, upgrade or downgrade as necessary. We are coming to the end of the presentation. So far we have seen the challenges with the existing networks, how they were very rigid, how they were capital intensive, human intensive, and how software defined networking presents a faster way to bring about networks, to manage your networks, and more importantly brings in choice. And over and above all of this, it gives you the user the freedom to innovate, the freedom to customize your network, your investment per your needs. The last slide on this presentation is all of the opportunities, things that we can solve with networking, with software defined networking. Obviously this is a subset, but if you are building a project, if you're thinking about your third year engineering or fourth year engineering projects, these are some areas that you can focus on to capitalize on some of the opportunities in this space. Through this presentation, I hope you had an opportunity to learn about SDN as a technology and the benefits that it provides as you go about building the next generation of networks. Thank you for watching this presentation.